There's some problem in these simple chirp mirrors. Group delay ripple. Okay? If you observe the simple chirped mirror, the green one is the substrate. Dark and the gray means N1, N2 periodic structure. You can see there is partial refraction at the front entrance. Okay? Incidence beam comes from the right-hand side. So hits the DBR structure first. There is partial refraction here. Okay? So you can plot a partial refractor here. And the design will ensure all the wavelength components will be eventually refracted. So that means almost 100% refraction by the entire structure. So you can plot a perfect refractor here. Okay? So a simple chirp mirror actually corresponds to a cavity consisting of one perfect refractor and one partial refractor. You have a cavity. And what happens if you have cavity? You have resonance, and the signature of resonance in the frequency domain is what? You have a periodic transmittance. Fabry-Perot interferometer, right? And actually, the periodic structure is not only for the reflectance, but also for the phase. 就是你印象中的那个 Fabry-Perot 周期性只是反射率的频谱，其实不止反射率是周期性的，那个 phase 也是周期性的。Okay, so that's the originality of the group delay ripple. Because you have a cavity structure, you have spectral ripple, so that's the case. For example, you want to design a simple chirped mirror with anomalous dispersion. So the blue line is the desired group delay curve. Longer wavelengths, larger group delay. Okay, that's your target. You want something like the blue curve. But after you perform the simple chirp mirrors, you actually got the red one. In average, it's correct, just like the blue curve. But in detail, it's serious rippled. Your group delay is not a monotonically increasing function as you want, but jump up and down rapidly. That's a big problem if you want to use this device for post-compression, right? 你可以想想看出来会是什么。比如说你原来的 group delay 是这样嘛，所以你希望用这个 delay 去 cancel 它，结果你弄出这个，那你出来会是什么？你可以想想看你会出现一个很乱七八糟的东西Okay, so that's the challenge, the problem suffered by simple chirp mirrors. So what's the remedy? 怎么解决？我们好像解决了一些问题，又制造出新的问题。这个 chirping 本来就是为了对付那个 standard DBR 有 GDD 就有 high loss 的问题，又制造出新的问题。You can double chirp mirrors. What is the meaning of double chirp mirrors? Okay. You need to chirp not only the period, as in simple chirp mirrors, but also the duty cycle. This is something new. What is duty cycle, to your knowledge?
The thickness ratio between N1 and N2.
Yes. For example, you have a square wave. You can control the duty ratio. 1 and 0, if 1 to 1, its duty ratio is 0.5. If 1, the time period of high state only 30%, low state 70%, you have a smaller duty ratio apart from 0.5. Okay. And here the duty cycle or duty ratio means the percentage of N1 thickness and N2 thickness. Previously it's 1-to-1, 50-50. But here, if you chirp it, it can be apart from 50-50. Say initially, this is 50-50, right? Long period, duty cycle is 0.5. You have a shorter period in the second one, and the duty ratio is apart from 0.5. You can see the dark thickness is relatively smaller than the gray one. And then you can have shorter and shorter period, smaller and smaller duty cycle simultaneously. That means double chirp mirror. 双重的 chirping. 既 chirp period, 又 chirp duty cycle. Okay, that's the double chirp mirror. But why do we need to chirp the duty cycle as well? What is the impact of chirping the duty cycle? If you think about the standard DBR, you should identify that the working principle of DBR lies on the quarter wave thickness. Okay, so 0.5 duty cycle means perfect quarter wave thickness. If the duty cycle is away from 0.5, that means partially violating the quarter wave thickness rule. And that means the local reflectance is reduced. 就是在4/4波长反射是最棒的，所以我们以前是用那样做设计嘛。Duty cycle 一旦不是0.5，你就部分违反了这个4/4波长的 rule， 所以你的 reflectance 会下降。Originally, we want to have a high reflector, so reduction of reflectance is something bad, something you want to prevent. That's why you have 0.5 duty cycle in principle. But here, we purposely reduce the reflectance in an attempt to suppress the partial reflectance here. You know, you have a cavity effect due to the partial reflector here, right? If you suppress the partial reflector, the ripple will be reduced. That's the central idea. And I can show you one example. In each figure, you have two curves. This one means the refractivity spectrum, referring to the left axis. And the ripple one refers to here, group delay spectrum. Okay, you see very obvious ripple. And the dashed curve means the average group delay. Okay, so if you use single chirped mirror, you got group delay distribution like this. Although the target is the smooth one, but you cannot have a smooth group delay. By using double chirped mirror, you got this. Okay, if you look at the group delay curve, okay, you see it's much smoother than the single chirp mirror, right? Almost just like the average result. Oh, 它有代价要付。虽然你看，哇，这里也接近100% 嘛，好像没有损失，其实它有损失哦。损失在哪里 ？Narrower bandwidth. in simple chirp mirrors, the reflection band is wider than the double chirp mirror. Okay, high reflectance only appear over a shorter wavelength range, smaller wavelength range. That's the price you have to pay. Should be normalized frequency or wavelength. I have to check. But is it reasonable? 为什么你用了 double chirp mirror， 你的有效频宽就变小？其实很自然了。你不是让这边的功能弱化吗？那这边功能弱化，它的 reflectance 会掉了。虽然它把你的 ripple 拿掉了，可是以这个设计来说，短波长或者高频可能就吃亏了，对不对？就你高频本来要靠这里反射，可是这边的 duty cycle 不好，不是0.5，所以它反射率会掉下来。你看，所以这个横轴应该就是 frequency。High frequency component corresponds to lower reflectance because of the double chirp. Okay? Last page. One example. Nowadays, chirp mirrors are very popular and very powerful. I just show you one example, very recent example. 1.9 femtosecond post compression. So this is the experimental data figure. Horizontal axis is wavelength. Okay. If you look at the reflectance spectrum here, okay, this is 100%. So you see all the wavelength components are above maybe 90% reflectance. The wavelength is from 0.5 microns, green light, to 2.3 microns. It's already mid-infrared. OK， 所以在这么宽的 wavelength range， 从绿光到中红外光，反射率都维持 90% 以上。Okay. Very efficient. Okay, but you might be more interested in the performance about group delay. Okay, there are many curves here, so I try to not to confuse you by making some notation. For example, the blue one, you see some rippled curve, right? The ripple contains blue curves and the red curves. For blue one, it corresponds to the group delay due to the first double chirped mirror, DCM1, number 1. Although you have applied double chirped mirror technology, but in reality, the group delay still has some ripple. 那当然，你是把这个纵轴的 scale 放很大，你才会看到这个 ripple。你把它 zoom out， 可能 ripple 就不明显。So that means even you have already used double chirp mirror technology, you cannot totally eliminate the ripple of group delay. But there is another solution. Why not to create another ripple but slightly detuned? Actually, properly detuned. So they use the second DCM. The red curve still rippled. And if you zoom in the figure, you can see the red peak corresponds to the blue valley, and vice versa. So detuned by half cycle. Then if you simultaneously access these two DCMs, so DCM1 plus DCM2. In practice, it means you have two DCM, double chirp mirrors, in parallel with each other. Shine the beam, hits the first one, reflected, hitting the second one and out. 你就 access 两个 DCM, 对不对? The total effect is the black curve. Now it's much smoother because of the proper dephasing or detuning, peak to valley. So the oscillation will cancel with each other. Okay? So this is the experimental result. The black curve means the input spectrum. The red one is output spectrum. So you see here, perfect overlap, right? So that means your refractivity is very flat and very high. 你才能够保证进去跟出来的 spectrum 几乎一模一样嘛，对不对？右边这一块有一点分别哈，就是长波长的地方红跟黑有一点点差别，那就是来自这里啊。因为在长波长的地方 refractivity 没有那么好了，也没有那么平坦了 ，so you can see some difference. But anyway, that means you have big and flat reflectance spectrum. Okay? And if you measure the output spectral phase, you see it's almost zero. This is zero. Residual phase is almost zero over the entire spectral range. That means your group delay curve is very perfect. So you got nearly perfect dispersion compensation. Okay? And if you plot the compressed after DCM1 plus DCM2, you have a compressed pulse. And if you measure the electric field, you got this. The solid curve means electric field as a function of time. But actually, there are two curves. Black one means ideal transform limited pulse. Red one means measured pulse. You can see they are almost overlap with each other. That means dispersion compensation is nearly perfect. Okay. The dashed curve means the absolute value of your temporal envelope function. And if you plot temporal intensity function, you got this. Again, two curves. Ideal, transform limited, and measured. They are almost overlap with each other. Pulse duration now is 1.93 femtosecond. Transform limit is here, 1.88 femtosecond. Okay, so if you have a well-designed chirp mirror set, not just single chirp mirror, a set of or a pair of chirp mirrors, you can do that. 就是 loss 很小，压缩的状况很好。Okay, so that's why nowadays chirp mirrors become very popular in pulse compression, especially in handling high power or high energy femtosecond pulses. 那它不用很大的空间哦，反正就是两个 mirror 嘛，间距不重要，只是里面的多次反射造成它的 chirp。啊，你用 grating pair， 你要很大的 size。Here, one more notation. It can sustain 1 millijoule pulse energy. Okay. So, in summary, what is the picture of angular dispersion? 什么是 angular dispersion? 你想要怎么对人家说明 ？What is angular dispersion? Whenever you heard of dispersion, that means frequency dependent or wavelength dependent. You see another word, angular, so that means frequency dependent direction of propagation. That's it. 你要试着会看着它的名字就把它的意义翻译出来啊，这样就很容易。Second question. Why can angular dispersion result in pulse chirp and intensity from tilt? There are two impacts. 为什么 angular dispersion 就会造成 pulse 的 chirp？ 不同的 color 出现的时间不一样，叫做 chirp。Why?
Past length.
Yes, good. The key word is past length. If different colors propagate along different direction, it can accumulate different path lengths. It will be transferred to different group delays or different phases. That's why you have post-chirp. Okay, good. But why there is intensity front tilt? Then you have to clarify what is phase front, what is intensity front. They are different. What is phase front? It applies to perfect sinusoidal plane wave. And it's referred to the carrier, right? Carrier is a sinusoidal plane wave. It has planar phase front, normal to your propagation direction. Okay? But you have many different plane waves propagating along different directions. So phase front only refers to the carrier. But the intensity front refers to the envelope, the superposition of all the colors. Okay? And our mathematical model shows the envelope will propagate along a different direction, which is first order derivative of your wave vector, not just the wave vector itself. That's why you have intensity front tilt. 因为你的 carrier 走的方向跟你的 envelope 走的方向不一样，就会出现这个结果。Question C. Why can a grating pair provide tunable dispersion? So now instead of just one grating, you have two gratings in parallel with each other. Why you can have tunable dispersion? Yes, then you can tune the path length difference. That's why you have, you can tune the dispersion. Dispersion comes from path length difference, frequency dependent path length. Good. What is spatial chirp? Again, you see chirp, that means frequency dependent or color dependent. You see spatial or space, right? That means position. So this means frequency dependent position. Okay. And if you think about the grating pair geometry, you can figure out why is that. 就是出来的时候高度都不一样。Finally, what are double chirped mirrors? You see chirp again. 我说 chirp 就是 frequency dependent or period dependent. Frequency dependent period 出现在不同的位置嘛 ，duty cycle 也出现在不同的位置，所以 double 嘛，双重的 chirp。Okay. Maybe we can conclude this lesson by comparing the performance of grating pair and the chirp mirrors. They are both dispersion compensators, but what are pros and cons between these two compensators? What are the advantages of grating pairs over chirp mirrors? Any advantage? Easy to fabricate. Maybe yes, but that's only for small gratings. For big gratings, it's still very difficult to fabricate. Okay. 那 chirp mirror 牵涉到多层膜的制成，的确很 tough， 没有错。但是大面积的 grating 要做得好也很难。Okay. Any other advantage? 如果没有 advantage， 它早就被淘汰了，对不对？它还是有 advantage。What advantage? Ripple? But can be partially solved by a pair of double chirp mirrors. as I just showed you. I think the most important advantage of grading pair is the group delay dispersion is tunable, not fixed. Just change the separation. You can have big or small group delay, but in chirp mirrors, you can't. After you have the mirrors, the chirp is fixed. Okay. So although it looks very perfect, you can compress high energy pulse with very low loss and with nearly perfect dispersion compensation. But there are a lot of effort behind or in advance. For example, you need to precisely characterize your spectral phase. If you do something wrong, after you have the chirp mirror, it does not work. Chirp mirrors are expensive. 你要很好、很精准的量测，你的瘦子要很稳都不会跑，这个才会有用嘛，对不对？那 grading pair 就不用嘛，反正变了我就调一调。那但是 grading pair 的缺点是它没办法补那么好，我们有讨论过嘛，2阶可以让你随便调了，3阶通常会变更糟。OK， 那还有呢，还有通常它的 loss 是比较大的。Grading 是 based on diffraction, right? Although you can rely on your design to purposely enhance a specific diffraction order, but that's not perfect. Some percentage of power will be wasted in other unwanted diffraction order. So your efficiency cannot be very high compared with chirp mirror. You see the data, chirp mirror can be 90-something%. If it's over a short, narrow bandwidth, it could be 99.9%, even higher. 刚刚那个是非常宽，所以你是90% 以上。如果频宽窄一点，它可以99.9%。Grading pair 不可能做到这种 efficiency. 所以 grading pair higher loss, worse compression, but flexible, it's tunable.